So, Niharika Sravan, are you there? Can you please?
Yep, I'm here.
Can you please share your screen?
All right, give me a second right here. Are you able to see this?
Yeah, perfect. So, can you show it full screen? Yeah, excellent. So you have 12 minutes plus 3 minutes questions. I give you a warning 1 minute before the end. Okay, take it away.
All right. Hi, my name is Niharika. I'm a postdoc here at Caltech. This is work we've done completed recently with collaborators at Caltech and other institutions. And I'm just here to talk about it. All right, here we go. So as we all know, we are entering the generation of surveys where there will be an unprecedented amount of data, and VRO is going to be the big game changer that's going to be entering the scene in a few years. And the change that actually is going to happen is in terms of the real-time delivery of the discoveries that it's going to make. And we are already doing it here at Caltech with ZTF, and obviously the Rubin Observatory will do this for a much wider landscape than we're familiar with. And there is tons of great science that you could be doing for transient astronomy. So like supernovae or electromagnetic counterparts to gravitational wave sources. But there's this realization that the data as is coming through these surveys will be insufficient for science inference. So here I have a plot for a very famous supernova, which you can see for which the light curve you can see in all the filters that were measured. So this is a well-studied supernova, and on the right is the same supernova, which is resimulated as if it were observed in ZTF in real time. So there is marked difference in the type of light curves you expect. And of course, it affects the analysis that you will do downstream. So there is cognizance that the data as is will be insufficient. So there will be some amount of follow-up that will be necessary to inform your science. And of course, there is some associated FOMO, which is that you can't come back and get the data. So if you have to make the measurements, they have to be done right now. And then you have to measure it against other competing science cases that you have in mind. So there is a need for performing value-driven follow-up in a real-time basis, and you have to do the explore-exploit trade-off along with many targets and any future observing opportunities that you may have. So one of the types of science cases that expect to see a huge transformation is supernova 1A cosmology. And we love supernova 1A because they help us get insight about the universe for dark energy. The low redshift samples that we're getting from ZTF can be useful for measuring H0 and local large-scale structure properties. And as such, we expect a lot of samples to be coming in. ZTF has already delivered over 4,000 spectroscopically confirmed supernova 1A as of today. I mean, as of recently, and the Rubin Observatory will do this way better in the future. So there's so much science and excitement coming up, and there are space telescopes that will probe these events in spaces. In observational spaces that we have not had access to before. So there's great science and great opportunity. However, as we are looking forward to doing precision cosmology, there are significant limitations. So if you think about it in terms of the uncertainties that dominate our measurements, there are two types that people usually worry about in this game. You think about statistical and systematic uncertainties. The statistical ones you can sort of more or less address when you get more samples. So your error will go down as 1/√n, where n is the number of samples. The systematics are sort of up to us as to how we fix them, and they have to do variously with various sources. So you have calibration, you have selection effects, you have the light curve modeling itself. So if you believe some of the results that are coming out recently, which tries to put numbers on each of these components, the SALT2 model, which is pretty much like very widely used in this type of work, has a huge contribution in terms of how much uncertainty it's contributing into your measurement. So for example, measuring the dark energy equation of state, the SALT2 model has about, the SALT2 model calibration has about 2 times the amount of uncertainty contribution compared to other groups of systematics that you may consider. So you can look at some work coming out of Dan Skolnick and collaborators for that. So if you think about sort of like getting the distance measurement for each supernova in order to do your cosmology, there are various sources of error terms, the uncertainty terms that come in. And the one that, is associated with SALT2 models, and, I'm going down this path because I'm going to eventually worry about the light curves, is given here. And since the errors sum in quadrature, it would be nice if you are able to minimize the error coming from the SALT2 models. There's the approach that we took for this was that, the Rubin Observatory is going to give us this tremendous opportunity. And there is a way to actually take action in real time to respond to the specific science constraints that you have in mind. So going back to the previous slide where I was talking about minimizing the uncertainty budget for a particular type of science case, if you're able to take action in real time for supernova 1A light curves to eventually minimize the uncertainties coming from the modeling, that would be very informative and good. We actually try to do this type of analysis for Zwicky transient factory supernova 1As that were classified. Now, of course, ZTF1 isn't the ideal candidate because, of course, you have just 2 filters for the public survey. And, you have a 3-day cadence, and we had it for the first part of the survey. So obviously LSST will be significantly sparser. So I think there is a better applicability for such a program for the Rubin Observatory. And I will show you a subset of results to sort of indicate that that might actually be the case. But nonetheless, to just sort of like get a sense of what is actually possible in real time, here's what we did. We had the Zwicky transient facility, the public survey light curves, and we tried augmenting them in G, R, and I, using P48. Now this is simulations. The reason we use P48 is because I have a good model for the noise model and the uncertainty model. So I have some reliability in terms of the photometry that I will augment. And the reason I include the I-band in the public survey is because it's been shown that the I-band data is important for precisely estimating H0. And other studies like the one I have shown here, some of the results show that the properties in the Redder filters can actually constrain something about the explosion mechanisms. So this could include, the overall luminosity, the nickel mass, and so on. And I would also like to highlight that this project and the machinery behind it isn't specific to SALT2. It's actually quite broad. So if you want to put it under an umbrella, this is an optimal real-time resource allocation problem, and it's pretty flexible. So you can apply it to any other science target that you have in mind. And I will sort of allude to some of the science that we're going to think about. And obviously, I solicit any participation and any interest to see whether something like this can be applied to your science case of interest. So here's what we do. Your goal, obviously, is to that you're given an observing budget, and your goal is to be able to augment these light curves in real time, such that you maximize a certain reward that you get at the end of the light curves. So as you augment, your science goal isn't realized per photometry; it's actually realized at the end of the episode. And the important thing is that you need to be able to adapt. So as you collect data, if you've made mistakes or if you're not doing as well, you need to be able to respond to that. So as such, in decision theory, of course, utility conveys your preference for your outcome. And this is where you get to be the artist and decide what you want. In our case, because we were motivated by the cosmology question, we went after A optimality. Another caveat is that I don't assume through this process that I know the redshift, because for most cases, I don't think that we'll get a reliable handle on the redshift of the event. So we just go ahead and actually solve for it in the minimization process and try to minimize its uncertainty as well. And of course, you assume some sky location. And the way this is done is essentially you take the whole action space that you're considering at a given time. So in our case, it's G, R, and I, and in various combinations. And at every epoch, given what you observe and given what you expect to observe, you measure the expected utility against your utility criterion. Now, of course, the outcomes usually in this time series are stochastic. Which means that we don't really have a good guarantee that the sampling, the 3-day sampling will actually occur. So usually what we do is we perform several simulations for outcomes, and we consider the modal action with the highest expected utility at any given step, and we pick the one that has the least cost. The augmentation procedure, as I mentioned, is so once you choose your action, which is associated with the maximum utility, since this is a simulation, we augment the light curves with a 2D Gaussian process fit. And the outcomes associated with actions are estimated with an encoder decoder LSTM that we trained on 100,000 supernovae 1A. So here's the results really quickly. So here are just a bunch of examples of supernovae 1A that were augmented in real time. And off the bat, we find that usually these augmentations are strategized to be either gap filling or to resolve phases with high expected variability. So things where like around peaks and valleys. And given the budget, so here a budget is considered per supernova. So like, you get to, choose 6 photometry that you want to allocate from, and then you go ahead and you drop it as you see fit based on the algorithm prescription. And the median improvement over a random allocation for various parameters are as quoted. The interesting to note is that even if you're assigned a budget, depending on how you train the system, you may not be using all your budget at a given time. Yes, thank you. You may not be using all your budget. And apart from that, just looking at some statistics, if you look at how the augmentation looks like in particular bands, we find that usually we augment more when there is sparsity. So actually, if you look at supernova 1A that are fainter than about 18.5 mag, we have actually about 3 to 5% more improvement for those the fainter events. And that is, of course, because there is more augmentation when there is sparsity. And actually, this plot delivers that information. So since I'm out of time, I won't go through this panel, and it's probably not critical. But so the good thing about doing this procedure was that this technique is interpretable. You know why the augmentations were taking place, where they were taking place, and it was a good start to try before invoking some reinforcement learning technique. And also, obviously, it was good because it gives us good benchmarking. And at this moment, obviously, we really need to verify this technique with real data to verify the robustness. And there are various extensions of the work that you could consider. So obviously here, the observing cost was 1 per observation, but you may want to consider sort of like exposure-based costs, or you want to have your budget described over an observing season. And then obviously, we may want to consider any latency associated with data acquisition or any failure that you may expect that you may get by your observation not being observed. And then, of course, that we're interested in extending it to many other science cases. So one thing that's of interest here is to be able to follow up kilonova observations, and then you allocate your budget best to get the optimum science gain. Now, of course, this is a harder problem because kilonovae are extremely fast and much poorly characterized compared to supernova 1A. But of course, there is significant great utility to actually go after these targets because so little is understood. So yeah, I was happy to present, and thank you for the opportunity. Please participate and let me know if you have thoughts, and I'm happy to hear from you.
Thanks, Niharika. Applause, please. So I'm opening the floor in the room for questions. Are there questions? Do we have questions on Slack? Okay, then I ask a question. So if I understood correctly, and I may not have understood it correctly, you assume that you don't know the redshifts of the supernovae. but could you basically exploit the correlations between them through the cosmic flows and so on to basically reduce that uncertainty in your model?
I think there are a couple of ways to do this. One is actually doing this on the fly. So somehow having your algorithm make these deductions on the fly for sure. I'm happy to like explore what this would entail specifically if you're able to elaborate on it. But I do want to say that there is the expectation that especially for a cosmology sample, you will have the opportunity to get a redshift at a later time. So we actually do repeat the analysis by using the spectroscopic redshift, as was mentioned, in a hindsighty way, even though the particular decisions for augmentations weren't designed around the availability. We actually go ahead and see what the improvements would be for cosmology, and the gains get reduced slightly. But then of course, if we get the full information, which we're going to process the light curves eventually with anyway, that would help you make better decisions on the fly. So anything that we could incorporate reasonably, and of course, if it would be has some sort of uncertainty, or say, for example, you may not get it for the entire population of supernova 1A, you could factor it into your process, saying, okay, you know what, I don't think, so for example, this would be sort of my false positive rate or something, and you incorporate that in your calculation. That would be an interesting extension for sure. So I'm happy to talk about it. Yeah.
Thanks a lot. We have a question on Slack. One second.
Okay, so very nice talk, thank you. In this work, do you already assume you know the class of the events before running the procedure? As in, you do not know the redshift, but know that it is an SN 1A?
So the answer is no. I assume everything is a supernova 1A, and I will augment it as if it was a supernova 1A. So as the event was happening, if I do not include other information, it would just augment it meaninglessly, and it would respond to the supernova 1A goal, and it will fail. So yeah, there is opportunity to include additional information, but since I wasn't sure I could get reliable broker information early enough, and plus, this is such preliminary work, I just wanted to see what would happen if we tried it, that I haven't tried incorporating that. So if you will look at some of the plots later on, you will see that a lot of the augmentations actually occur around the first peak. So the fact that, whether we would get reliable classification at that point, photometrically speaking or otherwise, is a question. But then since supernova 1A are so dominant, if you went after the goal, a lot of the times you wouldn't be wrong because they're so enormous in number. But it's definitely something to consider as you extend the program, especially for kilonovae and such. Would be an important consideration to have when going after targets.
Okay, thanks, Niharika.